Okay. Okay, I'll start off by describing a summary of the types of bridge management systems. Okay. I'll start off by talking about the types of bridge management systems that are in use in the USA and Canada. And then I'll get into some examples from some of the capabilities of these software systems and talk about some of the implementation issues concerned with getting these systems and putting them to work in a transportation agency. And then I'll finish up with some examples of how different states and provinces in the two countries have customized bridge management systems for their own purposes and the kinds of research that they've been doing to improve their bridge management systems as they get more experience and more data. Now in the USA and Canada, they're kind of similar in that each of the states and provinces manages its own bridges. There isn't really a national bridge management function in either of these two countries. Of course, the United States has 50 states, and Canada has the 9 provinces and territories. So each of those pretty much does its own thing. On average, in the United States, each state has about 12,000 bridges. That includes any bridge or culvert with a maximum span length of at least 6.1 meters or 20 feet. It doesn't include some of the smaller structures, but some of the individual states do include smaller structures, sometimes down to a length of 6 feet or 2 meters in span length. So the states do vary in what they consider to be a bridge. I understand from talking to people here that Costa Rica has somewhere between 7,000 and 10,000 bridges, and that would make Costa Rica very similar in size to a typical state in the United States. The Canadian provinces have somewhat smaller number of structures in each of the provinces, and the average in Canada is probably pretty close to the number that I've heard from Costa Rica. In the USA, there's one bridge management system software package that is used in most of the states. It's called Puentes, and 44 states now are using that for their bridge management purposes. There are 6 other states that have developed their own custom bridge management systems entirely from scratch. Whether it makes sense to develop an entirely new system is certainly a matter of debate and has been debated many times in the United States and in Canada. To give you an idea, for a state to obtain the Puentes software costs about $30,000 per year. For a state to develop its own bridge management system has typically cost on average of $6 million. So there's a bit of a cost difference between developing your own or licensing one that has already been developed. And of course, the reason that a package like Puentes and also the Canadian system are relatively inexpensive is that the costs are spread out over many agencies. So each agency doesn't have to spend as much. Now, Canada has 5 provinces using a software package called the Stantec BMS. Stantec is an engineering firm that is based in Canada that has developed a system that was originally developed for the province of Ontario and then was expanded for the province of Quebec and now is in use by 5 of the provinces. And 2 of the provinces, British Columbia and Alberta, have their own bridge management systems that they have developed themselves. And the other territories are not using a bridge management system at all at this point. Many cities in both the United States and Canada also have their own bridge management systems. They're either using Puentes or the Stantec system to do local bridge management. What many of the states do in the United States is the state will administer the bridge management system on behalf of all of the government agencies in the state. the local governments then can use the database and take advantage of the technical capabilities of the state government so that the local government doesn't have to have those capabilities in-house. Because of course many of the city governments don't have bridge engineers and don't have software development capabilities of the sort that a state government would have. I'll start off by describing the bridge inspection process. Of course, when you first get a bridge management system, the first thing you want to do is get data into your system about all of your bridges. And that's not as easy as it sounds. Many agencies, when they've started in bridge management, and this is especially true in Canada, really did not know how many bridges they owned. They had a vague idea of how many they owned, but when you especially get to the local government level, there are many cities that really haven't a clue how many bridges they have. In the United States, that was not as much of a problem because of federal legislation that was passed in the late 60s that forced each state to make an inventory of all of its bridges. So because of that state law, or that national law that applied to the states, we had a pretty good inventory in the United States already when Puentes was developed. In Canada, there was no such law, and so it was necessary in Canada for each province to figure out, first of all, just what bridges it owned. Once you have an inventory, then you can start planning an inspection process. Now, in both the United States and Canada, it's typical for a bridge to be inspected once every 2 years. A few of the states inspect their bridges every year, and also there are many cases with certain types of bridges, especially concrete culverts, where the bridge may be inspected less often, simply because they don't deteriorate very fast. Not much happens to them in 2 years. So they would be inspected less often. In the United States, the inspection process is governed by an inspection manual that is published by the American Association of State Highway and Transportation Officials, AASHTO, which is an organization you may have heard of because they publish a lot of documents that are used all over the world, really, but of course mostly in the United States. So AASHTO has a manual on bridge inspection. It's in its third major revision right now, and a fourth one is in the works that is going to be voted on about 3 weeks from now. So if the states vote to adopt the new manual, then we'll publish a fourth edition of the Bridge Element Inspection Manual. There's also something called the Federal NBI Coding Guide. NBI stands for National Bridge Inventory. That guide has been in existence for a long time, and it's been almost 20 years since it was last revised. So it's quite stable, and that governs the basic inventory of bridges and a few of the condition items, but the AASHTO Element Inspection Manual is what really describes the important condition information that we need for bridge management purposes. In Canada, Canada doesn't have the same way of standardizing different kinds of business processes the way the United States does. It doesn't really have an AASHTO per se. It has the Transport Association of Canada, which tries to get the provinces to cooperate on different efforts, but it's not always easy to do. The Canadian provinces really like to do their own thing. So Ontario did develop a very good bridge inspection manual called the Ontario Structure Inspection Manual. That was adopted by several of the other provinces, so now it probably, if there's any sort of Canadian standard, that's probably it, even though some of the provinces still don't use it. So Canada has something that may become a standard, but is not quite there yet. So that gives us the condition information. In both of the US and the Canadian manuals, the condition is collected in the form of elements. Now, an element could be something like a bridge deck, or an expansion joint, or a bearing, a concrete girder, or a column, or a pier cap. Those are all examples of elements that are inspected on bridges. Each of those elements is looked at visually, and the inspector, by looking at the element, will code the element in terms of the severity and extent of deterioration. If the main deterioration mode is corrosion, then the inspector will determine how much corrosion exists in terms of a quantity, and then we'll record the quantity at several different severity levels. So the most severe corrosion might be section loss, where a portion of the metal is gone and the strength may be impacted. There might be less severe levels of corrosion that may imply future section loss, but maybe are not affecting the serviceability of the bridge at the moment. So the inspectors record all that information in a standardized way, and it ends up going into the bridge management system database. At the same time, each bridge is assessed for its geometrics, such as the lane widths and the shoulder widths and the curvature of the road. Those are all things that are correlated with accident risk. They also look at clearances, horizontal and vertical clearance, and they look at the load capacity. Each state has a process of assessing the load capacity of a bridge, doing structural calculations in order to determine the weight of a truck that can use the bridge. So that information also is recorded in the bridge management system. All of that functional information is used in order to determine what trucks are able to use a bridge and what trucks are not able to use a bridge. Of course, if a legal truck is not able to use a bridge, it'll have to take a longer route to bypass the bridge, and then if they do that, then a cost is incurred. They'll have longer distance, they'll consume more gasoline or diesel, and they'll take more time from the driver of the truck. So all of that stuff has a cost if the bridge is not capable of carrying all the traffic. And then finally, we also look at risk. This is a relatively new thing that we're doing in bridge management. We're still learning how to do this. But the kinds of risks that we look at are hurricanes, tornadoes, wildfires, earthquakes, floods, and we also look at certain man-made hazards such as advanced deterioration, fatigue, and collisions. So a bridge with advanced deterioration, for example, it's more likely that if an overweight truck tries to use the bridge, it may damage the bridge or cause it to collapse. So there's a risk associated with that the service of the roadway might be interrupted. So we look at all those kinds of risks. When you have a large inventory of many thousands of bridges, you can start to look at these uncommon events and actually see patterns and start to assess the overall level of risk on each bridge, relating the possibility of a service disruption against the characteristics of the bridge. And so we do that kind of risk analysis now in some of the states. Florida in particular has a pretty sophisticated risk analysis program that looks at all of these different types of risks to assign a value to the risk in terms of dollars, which they can then use in setting priorities for mitigating the risks or replacing the bridge if the risks are too high and can't be mitigated any other way. There are a couple of examples of bridge inspection forms, just to give you an idea of what they look like. You don't have to try to read these forms. But there's basic inventory and geometric information, location information. Every bridge inventory in the USA and Canada has GIS location referencing and linear referencing so that it can be located on a road network and on a map. Some of the systems, and I'll show you an example a couple slides down, some of the systems are interfaced with Google Maps and will show the bridges on a map. Geographic analysis is not quite as useful with bridge management as it is with pavement management, but it's still a handy convenience feature for seeing patterns and just for finding bridges that you're looking for when you're trying to browse through the database. Now, bridge inspection processes can also deal with things other than bridges, and some of the states have done quite a lot of this, looking at smaller culverts, looking at sign structures that hold up the roadway signs. Some of those structures are pretty large. Looking at retaining walls. Many states have very large inventories of retaining walls, and also looking at tunnels. And each of these can be inspected by the same sort of inspection process that is applied to bridges. To give you an example, in Florida, Florida has about 12,000 bridges that qualify by the conventional definition of bridge, but there are 33,000 structures in its database. All of the rest of the structures besides those 12,000 bridges are things like sign structures, traffic signal mast arms, and high mast light poles. Those are all things that they routinely inspect on the same interval as bridges and using the same business processes and the same trained inspectors. Speaking of training, by the way, the states aren't all the same in how they train their inspectors. Some of the states, like California, use civil engineers to inspect their bridges. So they send out to the bridge somebody who not only records the condition of the bridge, but also is qualified to make recommendations about maintenance actions and even design those maintenance actions. Now, other states, like many of the states in the middle of the country, do not use civil engineers to inspect. Instead, they use technicians. Typically, a technician will have 2 to 4 weeks of general bridge inspection training, and then they may have some additional training on more specialized types of bridges, such as underwater inspections to look at the parts of a bridge that are underwater. Those inspectors are not qualified to make maintenance recommendations necessarily unless there's something really obvious, but they do record the conditions that they see and they take measurements, so they gather a lot of the basic data. That kind of process is really useful in the middle parts of the United States because there are a large number of very small bridges with low levels of traffic on them. And so if a state has 50,000 bridges, but the vast majority are very small bridges, then it makes sense for them to send out lower cost technicians to do most of that work. But other states like California or Florida, they send civil engineers out. Their bridges are larger and have more traffic, and there's more risk associated with making a mistake in how they collect their data. So some of the inspectors are qualified to make work recommendations. And in this case, this is an example, and again, you don't have to try to read this, but this is an example from the city of Hamilton, Ontario, which is using the Stantec BMS. They use engineers to inspect their bridges, and their inspectors not only record the types of maintenance work that are necessary on the bridge, but they estimate the cost also for that work. And typically, that cost then is used in, is put together with several other bridges and put into a request for proposals where they'll go out to contractors to actually do the maintenance work that is needed on the bridge. And that's a pretty common business process, especially in city governments. Now, every bridge management system has a way to navigate through the database. Here's a typical example from Puentes. You'll have a list of bridges, and this list could go on for a long ways if a state has 12,000 bridges. So there are features to filter and sort the list so that you can find the bridge that you want. Once you've worked with a bridge inventory for a long time, you get so you know all the bridges by their numbers, and then you don't necessarily need to search for them. You just type in the number. But when you're first getting started, you usually can't do that. So it helps to have maps and other kinds of presentations to find the bridge you're looking for. So this is an example of a customizable listing of bridges. You can decide which data items you want to show, and you can sort and group and filter in different ways. Then when you click a bridge, you can see a photograph of the bridge as well as some additional inventory and inspection information about the bridge, which will help you look up important information quickly and easily, as well as make sure you have the bridge that you're looking for. Both of these systems, as well as the customized systems in some of the states, have features to store photographs. Some of them store design drawings for bridges. It's surprising how many states don't have design drawings in any sort of electronic format for their bridges, but that is slowly changing. You can use this screen also just to get access to all of your documentation about your bridges. The Stantec BMS has a tree structure desktop, so the data is organized into trees, so you can expand a district to see the bridges in a district, for example. And using that mechanism, you can easily drill down to find a set of bridges that you might be interested in looking at. One thing I should mention is that both of these systems can be implemented in Spanish. The Stantec BMS already has been translated to Spanish for an agency in South America. I can't remember which one now. It hasn't been implemented there yet. So it's already been translated. The Puentes system can be translated to Spanish, but that has not been done yet, but it can be. Analysis results can also be displayed along with bridge inventory data. The Stantec BMS in particular has a lot of capabilities to compute life cycle costs for a bridge, to look at different alternative actions that might be taken on a bridge, both the scope of work and the timing of the work, how soon the work needs to be done. And it will do that analysis based on life cycle cost and risk to show you the possible future for the bridge. Later on, I'll also show you an example from Florida where they actually have developed a digital dashboard that serves the same purpose as an add-on to Puentes to let them see at a glance the possible futures for a bridge. Here's an example of a GIS interface, this one from the Stantec BMS, where they connected up Bing Maps to the Stantec BMS. So using that, they can color code the different bridges by different characteristics and show how they relate to each other on a route, how they connect. One of the things this feature is especially useful for is traffic planning. When you do work on a bridge, you often have to interrupt traffic or take lanes out of a traffic stream on a multi-lane road. And so then you have to figure out where's all the traffic going to go. So you certainly don't want to take two parallel routes and interrupt traffic on both of them at the same time. So this kind of interface just helps you with the planning to make sure that you have a reasonable routing for all the traffic that might have to be detoured because of bridge work. As I mentioned, these systems have document management. When an inspector goes out to inspect a bridge, he'll typically take a lot of photographs. The document management system will relate each of those photographs to the bridge and possibly even to a particular element or a particular distress on the bridge so that it's easy to find that information in the future and get back to it. A lot of states now are using electronic data collection, and the simplest form is just a tablet computer or a smartphone that the inspector brings out in the field and uses to record the information that they're seeing. There is even a simpler form that has been in use for some time in a few states where if you have a two-person team doing the inspection, perhaps one of the inspectors will be out on the bridge looking at the deterioration, and he'll talk to his partner on a walkie-talkie. His partner is in the truck with a notebook computer and is just writing down everything that the first inspector tells him. So that's a simple way of doing electronic data collection. A little more elaborate way is using systems such as the Stantec system or several different devices that Bentley sells for Puentes, where you can record what you see on the bridge. Some of these are ruggedized tablets and notebook computers, and increasingly we're seeing a lot more use of smartphones for this purpose. Now, another kind of electronic data collection is this little guy, and actually there are quite a few different data collection devices like this, but this is probably the one that everyone is talking about this year. This is what is developed by the Federal Highway Administration Long-Term Bridge Performance Program, which is a long-term program to try to understand better how bridges deteriorate over time. They've developed a robot that they use to do bridge deck assessments. And it just uses a ground penetrating radar and as well as a few other sensing devices, runs it over the bridge deck to try to develop a good global assessment of the condition of the bridge deck, including the subsurface condition of the deck. Decks often deteriorate from the inside out. Chloride contamination causes the reinforcing steel to expand due to corrosion, and that causes pieces of the deck to come loose. So that there are delaminations within the deck structure that need to be detected, because eventually those will break up and become potholes and start to become a safety hazard or interrupt traffic. And sometimes in the northern states where they use a lot of de-icing salts, this deterioration can happen really quickly, and you might even see punch-throughs where the entire thickness of the deck has fallen out. And in fact, in some of the states that are not very good at maintaining their bridges, they have nets strung under the bridge to catch all the concrete that falls from the deck so it doesn't fall on the cars underneath. And so that's an emergency measure that they take if they can't even scrape together enough money to repair their bridge deck. And that is surprisingly common in some of the northern states. Now, all of the bridge deterioration models, I'll talk a little more in a moment, all of the bridge deterioration models that we use today are empirical models. So in other words, they're based on a very small amount of condition data. We use statistical methods to correlate condition and characteristics today with conditions in the future, but there isn't really a mechanistic basis for those models. Now, with devices like this robot and other research that the Long-Term Bridge Performance Program is doing, we're hoping to get a more mechanistic understanding of bridge deterioration. So you've seen some good presentations earlier about pavement deterioration and understanding how the mechanics of what happens to a pavement. We're not that advanced in bridges yet. We want to get there, but it's going to take some time, and it's going to take a lot more research to get there. One of the big problems is not having enough data, and so devices like this robot will help us to gather more data so we can develop those models. I mentioned risk assessment as an important part of bridge management that is starting to become more common now in the United States and in Canada. There are a lot of different kinds of risks. If you look at Florida, they have a very advanced risk assessment system, but they don't get earthquakes, so they don't really care about earthquakes because that just doesn't happen there. Now, Costa Rica is a little different from that. You get a lot of earthquakes. California also, of course, gets a lot of earthquakes, and my own state, Washington, gets a lot of them. So we do our risk assessments looking very closely at earthquakes, and we don't care about hurricanes because we never get those in the western states. So you know, every agency has their own concerns about what the risks are to disrupting their service, transportation service on the road network. So everyone looks at risk in a little different way. But the main components that we try to quantify are the likelihood of a hazard in terms of a probability. What's the probability that a hurricane of a certain category will take place at a given location? And then if a hurricane does occur, what's the consequence to the structure? What kind of damage would typically occur to a structure because it was struck by a hurricane? And that, of course, depends on a lot of things. Is the structure in a place where a storm surge may hit it? If it's along a river, will the hurricane cause flooding that might wash out the bridge? There are a lot of different things that can happen, and we have to look at those bridge by bridge to assess the risk to each bridge. Then once we come up with the consequence to the structure of what kind of damage might happen, then we look at what's the impact on the public. Some types of bridge damage are not that important to the public, and of course other types of damage may completely wipe out the bridge, and that it might have a big impact on the public, especially if it's a high volume road. So we look at that. And if we multiply likelihood times consequence times impact, we get an assessment of total risk, which we can use then in identifying actions and setting priorities. We look at functional deficiencies in terms of what kinds of traffic are not able to use the bridge because the bridge just doesn't have the capability to carry it. We start off looking at legal truckloads. These are the trucks that are loaded up to the legal load limit. Now, in the United States and Canada both, most of the states have pretty good enforcement of truck weights and truck dimensions. If your enforcement is not as good, then the way you would manage these sorts of things would be a little different. You would treat it more as a risk and less as an enforcement type of mechanism. But in the USA, we typically can assume that if the bridge is posted for a certain weight of truck, that there's only a small likelihood that a larger truck will use the bridge. But there is some likelihood, and we have to try to quantify that. And then we mainly want to quantify, though, how many trucks will obey the signs and avoid using the bridge and be inconvenienced because of that. So we quantify all of that, and we convert it into a user cost in terms of the cost of fuel and the cost of a truck driver's time. We put it into dollars, and then we can use that in a benefit cost analysis and as part of a life cycle cost analysis for the bridge. Now, a number of agencies have developed dashboards in order to give them a quick look at the current condition and future possibilities for a bridge. This particular example was developed in Quebec. It shows the increase in risk over time on a bridge because it's fairly deteriorated, and it shows the deteriorated conditions. All the oranges and yellows and reds in the bottom of the chart are bad conditions. If there were good conditions, they would be green. This particular bridge doesn't have any good conditions on its elements. And you can also see on this chart the history of bridge inspections on the bridge and some of the functional deficiency and risk indicators, as well as the life cycle cost calculation. So this was done for Quebec, and of course was developed in French, but it was built on top of the Stantec bridge management system, which was originally developed in English and then translated to French. And it was developed in Microsoft Excel. So it connects to the BMS database to get the data, but all of the other modeling is done using Excel formulas and Visual Basic code. So this is the sort of thing that can be developed where you can start simple, make it more elaborate over time, and that typically is what happens in each agency. They develop a simple spreadsheet, and then they want it to do more, so they add on to it. Eventually it becomes kind of disorganized, so then they redevelop it. When you do this kind of work in Excel, it's fairly low cost to do that. So state agencies like to work in that way to expand their bridge management system. Here's another example of a dashboard, this one in Florida, where Florida, of course, is a user of the Puentes bridge management system. The Puentes system didn't do all the things that they wanted for their own management purposes, and so they developed a spreadsheet to fill in the gaps, to take care of the additional capabilities that they wanted in their BMS. That also has expanded over time. Their first dashboard was developed in Excel in 2001. And then every 2 years since then, they've released a new version of it with new capabilities. And mostly those new capabilities were a result of research that they did. So initially they did some research on user costs, particularly on accident risk to associate crash rates with characteristics of bridges. And then they did some work on deterioration and on preservation costs for different kinds of maintenance and improvements to bridges. Then they took a special look at movable bridges because they have about 100 of those in the state, and those are bridges that have a lot of costs associated with them. And then just recently they went back and updated their deterioration models using their historical bridge inspection data to develop even better models, and they put those in their digital dashboard. And then they're just finishing up right now a risk model, which they've also added to their digital dashboard so it can do a full risk assessment on each bridge. So over time, they've expanded it, and they have a really nice system now that they've built just piece by piece over time with small research projects. Here's another example. Minnesota is another state that does a lot of work on risk analysis. So Minnesota developed a simple system for color coding different kinds of risks and comparing them from one part of the inventory to another. Their system can show risk county by county on a map of the state of Minnesota. This also is a Microsoft Excel application. It was all done as a spreadsheet. Minnesota uses Puentes, and this was just, this spreadsheet just accesses the data out of Puentes and does some more analysis and then presents the results. They present this information to their state legislature when they're trying to explain, when they're asking for money to repair their bridges, what will the money be used for, and what kinds of improvements in condition or risk can they expect from that investment. Here's another example, this one from the state of Alabama. This is actually a pretty old system, but they're in the process finally of updating it to some more modern technology. In Alabama, they have a lot of trouble with scour. When they get a flood, or even some streams are just naturally fast flowing, they move the material under the bridge foundation, and sometimes the bridge foundation will lose its support, and it could settle or collapse as a result of the loss of foundation support. So in order to get some control over that process, they go out with divers and other kinds of equipment to measure the scour profile under the bridge, and they track it over time. So they can see how the material under the bridge foundation is changing because of storms and floods and just normal water flow over the course of a 2-year period. And so they can follow that, and they can use that to make some predictions if historic patterns hold. They can start to make some predictions about future scour and use that to plan work to mitigate the scour or to replace the bridge in some cases as a result of scour. And that's all. It's a nice graphical interface here so that they can see what the scour looks like, and they can explain to local governments and other non-bridge engineers what they're talking about when they talk about scour and what it looks like. Because of course it's underwater, nobody ever sees it, and if you can't see it, you don't think it's a problem until the bridge falls down. So it's necessary to come up with a way to explain this to people. Now for decision support, one of the key things that we try to do in all of these bridge management systems is to try to minimize long-term costs. Now, what this little graph shows is that it's possible to do too much maintenance or not enough maintenance. If you don't do enough maintenance, which of course is the more common situation, then you end up with large long-term costs because the bridge won't get its full design life. You'll end up having to replace it sooner. And if you're doing a lot of bridge replacements, that just costs a lot of money because replacing a bridge costs a lot of money. In the USA, it's very typical to spend $3 million to replace an average bridge. And so you don't want to be doing a lot of that if you can help it. So it's expensive to not do enough maintenance. But of course, you can also do too much maintenance, and if you do too much maintenance, you also, of course, are spending too much money on maintenance. So what you want to find is the happy medium. That's the place where the costs are minimized, where you're not doing too much and you're not doing too little. You're doing just the right amount of maintenance. So we try to quantify that, and we do that with deterioration models and with cost models. To forecast what the future maintenance needs are and what the optimal time is to intervene. Here's an example of what a deterioration model looks like. We've done quite a lot of analysis in Florida. They have now 15 years of bridge inspection data in their Puentes database. And with that much data, we can do a lot of great analysis. They have more than 1 million element inspections in their database. So we can do some really good statistical models. We can start to look at cause and effect a little bit, even though these are still empirical models, to understand what things affect deterioration. We've also done a similar study in Virginia, and so we can compare models in Florida and Virginia because their business processes are different. Florida never uses de-icing chemicals because things hardly ever freeze there. Virginia, on the other hand, does get a lot of snow and ice, and they do use de-icing chemicals, and those cause things to deteriorate much more quickly. And we can quantify that now with the data that they have. So this kind of analysis is one of the things you can do with the bridge management system once you've been collecting good data over a period of time. Another thing that we've done in Florida is to analyze the onset of deterioration. Now, normally in deterioration models with bridges, because we're collecting condition state data, it's natural to use a Markovian model because that's pretty much the simplest possible model that can work with this kind of data. And Markovian models work okay, but there are ways to improve on them. And one way is to look at the onset of deterioration. In most cases, a bridge spends most of its life in pretty good condition before it starts to deteriorate. But once it starts to deteriorate, then it tends to deteriorate at a faster rate. And so the later stages happen much faster than the early stages. And we want to make sure the model reflects that accurately. And a Weibull model is a really good way of doing that. It gives us a good, accurate picture of how slowly or quickly the deterioration starts in a bridge's life. So we did a lot of research on this in Florida and came up with some good models. They're not built into Pontus yet, or in Stantec BMS for that matter. So only Florida is using these models right now. But they soon will be implemented in Pontus, and then it'll be possible for any of the states or any Pontus users to make use of this type of model. So now it's really a hybrid of Weibull and Markov models that Florida is using that seem to work pretty well, giving them accurate predictions that agree with their historical inspection data. So we looked at the beginning of a bridge's life. We also want to look at the end of a bridge's life. What happens when the bridge gets in really bad condition and then eventually has to be replaced. We look at that in terms of risk. If a bridge is in really bad condition, as long as it's strong enough to carry the traffic, maybe nobody cares that it's in bad condition. But the reason people do care is that there's a possibility that an overload will cause the bridge to come down. Or at least be badly damaged and not able to carry any more traffic. So we look at advanced deterioration in terms of the risk that service will be interrupted. Florida, again, has done this research. It is based on a history of old bridges that have been already torn down and replaced, but they keep those in their bridge management system. They actually hang on to that old data when they tear down bridges and replace them. So we were able to go back and look at those old bridges and find out why they were replaced. And of course, they get replaced for lots of reasons. The most common reason is that they need a new bridge that's bigger, that has more lanes, or that is safer, or has better alignment. So that's the most common reason, a functional reason. But the second most common reason is the bridge was just badly deteriorated and it wasn't cost effective to do maintenance on it anymore. So the most cost-effective solution was to replace it. And they also get some bridges that are replaced or destroyed because of hurricanes or other kinds of risk-related hazards. So we did an analysis of that. We separated out the bridges that were replaced primarily because of deterioration, and then we looked at the correlation between that, between the condition and the replacement. And developed a log normal model. It turns out a log normal model is a very good representation of the behavior of a badly deteriorated piece of infrastructure. So that gave us a good risk model for advanced deterioration that agreed again with their historical data so they could make decisions based on that information. Now, all of this kind of information, as we're doing all this analysis of life cycle cost and functionality and risk, all needs to be used in decision making in order for anyone to want to do this. And so one of the things the bridge management system does, after it looks at each bridge individually at all the life cycle costs and risks and so forth, then it adds those up over the whole inventory and looks at uncertainty in things like funding levels and climate conditions to help understand future funding needs and how those might vary with things that might happen, so that they can start to inform decision makers in the state legislatures or in the executive branch of the government. They can start to inform them how much money they're going to need to keep bridges in good condition and what will happen if they don't get the money. And that's really important. You need to tell decision makers in a very quantitative, honest way what will happen if they don't get the money to maintain the bridges. Because if they don't understand that, they're not going to give you any money to maintain bridges. And then you end up, in the long term, spending too much because the bridge ends up collapsing or having to be closed, and then you're forced to spend money to replace it. Instead of being able to choose the time when you do the work on the bridge, and if you can make the choice, you'll do it when it's less expensive. And then finally, one of the more advanced things that we're doing with bridge management systems is called multi-objective optimization. Now we look at life cycle cost and risk and functionality and all these things as separate things that can happen to a bridge during its life. We need some way to combine all of those considerations in order to set priorities in a unified way. Because it's hard to answer the question, well, which is more important, earthquake risk or deterioration or heavy trucks not being able to use a bridge. It's hard to quantify which of those is more important unless you have some basis for that. And multi-objective optimization gives you that. So we've done some research on that. There's a report, NCHRP report 590, that describes a methodology for it. And that is starting to be implemented in bridge management systems now so that so we can look beyond just condition when we manage our bridges. And then another way that we use this in decision making is in the general field of asset management. You've probably heard this term, asset management. It's really looking at all the different kinds of assets that make up the transportation system. In most agencies, pavements are the biggest one and bridges are the next biggest one in terms of dollars spent on the asset. And then there are a lot of other ones. There are geotechnical assets, which add up to a lot of money, and drainage assets and traffic control devices and roadside features such as guardrails, and also in some agencies, buildings and equipment. So those all are types of assets that cost money and need maintenance and need life cycle planning. And they have a lot of performance concerns. The condition, of course, is the one that is obvious, but also how well they function, how available they are for service, the mobility they provide to the public, the safety to the public, the risk of service disruption, and then externalities such as carbon emissions or pollution emissions that result from the use of these facilities. So those are all concerns that an agency is trying to manage. And it does all this management through a number of mechanisms. These are the capabilities that they have. They have asset inventories, they have inspection and monitoring programs, they have systems for assessing performance and making comparisons, and especially in terms of levels of service. And then they have decision support programs that their management systems provide for forecasting future performance, estimating costs, deciding when to do projects and what to do in those projects, and then setting priorities and actually getting the work done. And they have to look broadly. It's not just a matter of mathematics and data and analysis. They need to look at their legislation and policies that in the agency, the things that govern how people do their jobs in the agency, their relationships with stakeholders outside the agency, such as legislators, the people who come up with the money, building better relationships with those people, and also building better relationships with interest groups and members of the public to build political support for getting the money to do the right maintenance on their infrastructure. And then within the organization, just having the support of the right functions, having the right people doing the right jobs in the organization, and having a culture where people actually care that their bridges are performing well. And many agencies, that's a problem, where you have a large agency with a lot of people, but their jobs are so unrelated to the product they're delivering to the public that they may not care that much what service they're delivering to the public. And part of asset management is helping them to understand better how what they do affects the public. So just to summarize implementation issues, I kind of talked a little bit about this already. Typically with the bridge management system, there are a number of things you have to do to set it up. You don't just buy a piece of software and say, I've got bridge management. It's a lot more complicated than that. You do have to buy some software, develop software, and install it. But then every agency needs its own set of reports to fit its own business processes. You need to adapt your inspection process to local needs. In the case of Costa Rica, when you adopt a bridge management system, it'll have to be in Spanish, of course, so that's one of the steps. You need to train your bridge inspectors and the people who are going to use the software so that you're getting good data and using it in the right way. And then, of course, having manuals and documentation so that so you can train new people over time. And so now Pontes and Stantec BMS are both systems that have been in use for a long time, and they're widely available. In the case of Pontes, they're actually renaming it. So you may see the expression AstroWare Bridge Management Software. For some reason, they decided that was a better name than Pontes. I still like the name Pontes myself, but they decided to rename it. So if you see the acronym BRM, they're talking about the future version of Pontes that they're developing now. It's the same thing. It's just a new version of the same system. My slide got messed up a little bit, but I meant to say gracias. And thank you very much for listening to my presentation. And I hope you found it interesting, and I'd be happy to take any questions.